Yes, friends, the new Turbo Ginsu. Woohoo! It dices, it slices, and yet makes French fries in 3 different. Whoops! Kids.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's very quickly review, and then I want to move on to some, I think, somewhat difficult concepts. My purpose in teaching these courses was to try to teach what I called the theoretical minimum, the minimum amount of stuff that you really need if you truly want to technically be able to go on to the next step. The next step, in this case, after general relativity, might be cosmology. And you really want to do it right, but you don't want to do everything. You don't want to do all the applications. You don't want to learn everything. You want to learn just enough, the bare minimum, to be able to go to the next step. Tonight, I think we're going to face the fact that the bare minimum is already a little bit complicated and requires some mathematical effort. It doesn't require advanced mathematics. It just requires patience to go through the calculations and to do them right. If I just told you in words what the answers are, I think I would not be giving you the minimum. I think I would be giving you less than the minimum. So today may be a little bit trying, but bear with it. What you get out of it, if you follow it, will be worth the effort. Okay, let's just go through the definitions of the transformation properties of the 2 kinds of components, covariant and contravariant. If I have a covariant set of components, covariant means lower, and they're now referring to a coordinate system y. Not only do I think of them as functions of y, but I also think of them as the components, the covariant components, relative to the coordinate axes defined by the y coordinates. Okay. So this is v sub m in the y coordinate system, both with respect to its components and with respect to what it depends on, y. Right? Those components can be expressed in terms of the components in terms of some other coordinate system. Here's some other coordinate system, x, y, and x. Given the components, the covariant components in one coordinate system, you can translate them to the components in another coordinate system. And here's the formula that we worked out last time, that Vm is related to Vn of x by multiplying it by dxn by dym. We worked that out last time. These are the set of objects that you use, and keep in mind that the summation convention is in force here, so summing over n. The open index on this side is m. So this side here is the mth component of v. The n index here is summed over, so it's just a dummy index, but on both sides you have an open index m. And notice that that open index m has to do with y. It's the mth y coordinate here. And on the left-hand side, this also has to do with y, because we're talking about the components of the vector in the y coordinate system. The x coordinate system, that's been summed over, and it appears only as a dummy index here. This is the transformation property of a vector. If it doesn't transform this way, it's not called a vector. Even if it has components, even if you might try building up an arrow to represent it, there's no question you can take, let's take the temperature, the pressure, and the humidity. There are 3 numbers. And I could now build myself a arrow which along that axis has a length equal to the temperature, along that axis has a length equal to the humidity, and so forth and so on. That object is not a tensor. It is not a vector. It's just a thing you made up out of three scalars. It's not a tensor because its components, when you go to a different reference frame, don't transform right. The temperature is the temperature. It's the same in all coordinate systems, and it doesn't change from one coordinate system to another. So the temperature does not transform like one of the components of a vector. In fact, it transforms as a scalar. All right, so any set of three numbers or four numbers, depending on the dimensionality of the space, does not constitute a vector. A vector is characterized by its transformation properties. Given it in one coordinate system, how do you get it in the other? Likewise, I'm using V now as the generic term for a vector, not necessarily the same vector. If I have a vector with contravariant indices, then it's related in the y coordinate system to the corresponding values in the x coordinate system by a similar formula, but now it's dy by dx, and now the n goes downstairs and the m goes upstairs. Look at the equations. You can't make a mistake about whether it's dx dy or dy dx. If you're talking about a thing with a covariant index here, it's got to match with a contravariant index here. On the left-hand side, you have a covariant m. On the right-hand side, you have a covariant m. And what's more, the covariant m on this side has to do with y. So the covariant m on this side has to do with y. So you can bet your boots that this one is going to be x in the upstairs. Same here. On the left-hand side, you have a contravariant index m, an upstairs index m, associated with the y coordinates, and that's why you have an upstairs index here, also associated with the y coordinates. So there's a pattern. That's the pattern of transformation properties of a vector. I won't bother writing down the transformation properties of a scalar. They don't transform. They're the same in every coordinate system. Yeah.
If it's a vector, it has to satisfy that top equation.
Yeah.
Does it have to satisfy the second equation?
No, don't identify this set of objects with this set of objects yet. This is just some covariant vector. Remember, I gave you some example of a covariant vector. The gradient, the derivative of a scalar with respect to a coordinate is a covariant vector. Don't try to think of now of the connection between covariant and contravariant. They're different objects for the moment. So I shouldn't have called them by the same letter. I just don't want to run out of letters, so I'll call them both V. Let's not. Let's call it W. Okay. This is the transformation property of a covariant object. This is the transformation property of a contravariant object. And they're not the same thing. Here's a covariant vector. An example of a contravariant vector would just be a small displacement, dx m. dx and dy representing a small little displacement. Well, dx1 and dx2. dx1 and dx2. Let's see, here's the x coordinates. Let's say this one is x1. Let's say this one is x2. You build yourself a vector by going off and making an excursion along the x1 axis by dx1, and then along the x2 axis by x2, and the resultant is the vector that we can just call dx. The vector that we call dx has components which are contravariant. Right? They're contravariant indices. The components of a gradient are covariant. And you can't go wrong. If you remember, the only rule you have to remember is that coordinates carry their indices upstairs. That's an arbitrary rule. It could have been the other way. But it's an arbitrary rule. I'm not sure whom it's due to. But you label the coordinates x1, x2, x3 with superscripts. And once you do that, it's hard to go wrong. Here's a superscript on an m, but it's downstairs in the denominator of something. It just looks like it has to do with something with lower indices. And in fact, it is true that this can be thought of as the gradient vector. Let me call it v again, v sub m. It's a covariant vector. dx has its indices upstairs. It's a contravariant vector. Now, the transformation properties came from the transformation properties of this object, right? Let's just see. If the vector we're talking about is a gradient, then this equation just says that partial of phi with respect to ym, that's the left-hand side here, because v is a gradient, that's equal, on the right-hand side, we have partial of phi with respect to ym, n, that's this object, times dxn by dyn, dym. Is this a correct equation? Yeah, that's a correct equation. d phi by dy is d phi by dx times dx by dy. This equation didn't come from the definition of any vector or covariant contravariant. It just came from elementary calculus that the gradient with respect to y is just equal to the gradient with respect to x times the set of components dx dy. That's elementary calculus, elementary multivariable calculus. But it's the place that we abstracted this rule. If I now call this Vm, and this one Vn, then that's my rule. Likewise, the transformation property of the contravariant vectors came from the statement that dym is equal to the partial of ym with respect to xn times dxn. Again, this here did not come from somebody's preconceived notion about how tensors should transform. It's just a calculus fact. What is it? Some sort of chain rule. They're both some sort of chain rules, I guess. And now, if I replace dym by wm and dxn by wn here, that defines, or this defines, the transformation property of a contravariant vector. That's where they came from. So covariant and contravariant mean things that transform the same way as gradients on the one hand and differential displacements. Differential displacements and gradients. Those are the sort of archetypes of covariant and contravariant objects. We can have more complicated objects with any number of indices. The transformation properties of objects with more indices are similar. Let me just give you an example. Here's a transformation property of a covariant expression. Supposing I have a tensor with two indices, let's say m and r. Then the rule is for each index, there's a factor of a dx by dy. And here's the way it works. This is t in the y coordinates. We're going to relate it to t in the x coordinates. Not mr, but we better choose some new, let's call it ns. And now, just as over here, to relate the m index to the n index, we need dx. This is a sort of operation which takes us from an n index to an m index. we do exactly that. dxn by dym. But that works on the first index here. We also need to work on the second index, and that's dxs by dyr. Now look at it. On the right-hand side, we have the components of the tensor, the rank 2 tensor, 2 indices, in the x coordinates. 2 lower indices. Those lower indices have to do with x. So on the right-hand side, it must multiply something with contravariant indices, again referring to x. But on the left-hand side, we have covariant indices referring to y, likewise on this side over here. That's the pattern. Indices are the things which transform, yeah.
Could you mix them or make any sense?
How would you want to mix them?
Some upper and some lower?
Yes, certainly. For example, you could have all right, let's do another example. Supposing we had a tensor which had one lower index and one upper index. Perfectly good object. How does it transform? Well, I should not have erased the transformation properties of the things with upper indices here. Let me write them down over here. So, here's for the lower index m, and let me change variable here. Let's call it RR. And now let's write the transformation property of an upper index, and that's going to be dyn by dxs vs. All right, so here's the thing with a lower index. Here's the thing with an upper index. Here's an object, a tensor with a lower index and an upper index. Right? How does it transform? Well, first of all, we have to work on the m index. That's going to give us a dxr by dym. And then we have to work on the upper index. That will give us a dyn by dxs times t. Now let's see, what is it? T. The upper index is s, and the lower index is r. All right, so that's the transformation properties of a thing with an upper and lower index, and it's just borrowed. It's just exactly the same as if you just stuck this thing next to this thing and thought of the tensor as just the product Vm, Vn. On the left-hand side, Vm, Vn referred to the y coordinates. On the right-hand side, Vr, Vs related to the y coordinates. All right? So that's the transformation property of a mixed tensor with some upper and some lower indices. And the general rule for any number of indices is similar. Okay, without this set of rules, it would be hopeless to try to explain the geometry of even a simple thing like a sphere in any great detail, but certainly a general geometry of arbitrary curvature, wiggles, and so forth, hopeless without tensors. So tensors are the key to understanding the geometry of curved spaces. Okay, let me point, let's do something else. Let's take a tensor which happens to have, let's take this tensor which happens to have an upper and lower index. And now let's identify and sum the upper index with the lower index. In other words, let's take TMM. That means T11 plus T22 plus T33, however many dimensions of space I have. T, one lower and one upper index. This is a legal operation to combine or to identify an upper index with a lower index and sum over them. I don't need to write the summation sign. I claim that this object with the indices identified and then summed. How many indices? What indices does this whole object have? Does it have any indices? No, it has no indices left over. They've been summed over. It doesn't have a T1. It doesn't have it's just a pure thing. It's a sum, and it doesn't have any leftover indices. What kind of thing is it likely to be? A scalar. All right, let's check that it really is a scalar. All we have to do is identify m with n. Let's do it over here. Set m equal to n, or n equal to m. We better do it over here also. I've set n equal to m. And sum. Now, what do we have here? We have the change in xr when we vary y times the change in y when we vary xs. What is this whole object here? Anybody know? That's the Kronecker delta. It's the Kronecker delta. It's really just the derivative of xr with respect to xs. The derivative of xr with respect to ym times the derivative of ym with respect to xs summed over m is the same as the derivative of xr with respect to xs. Just cancel out the ym. Well, what's the derivative of xr with respect to xs? It's like having three coordinates, x, y, and z. The derivative of x with respect to x is 1. The derivative of x with respect to y is 0. All right? So this is a number which is 1 when r is the same as s and 0 otherwise. In other words, it's just the Kronecker delta. We could replace this and replace it by the Kronecker delta, delta rs, 1 when r is equal to s, 0 when r is not equal to s. But now we're supposed to sum over r and s. What will that give us? It'll just give us the sums of T11 plus T22 plus T33 again. Whenever you see a Kronecker delta, it's really just a shorthand, or it's just an instruction to set r equal to s. Why? Because it's 1 if r equals s and it's 0 otherwise. So it's just an instruction. You can throw it away and in the rest of the expression set r equal to s. So look what we have. We have tmm of y equals trr of x. In other words, this particular combination doesn't depend on which coordinate system you use. The dependence of the components on coordinate system cancel out when you identify the upper index and the lower index and sum. That's a general pattern. If I have some tensor, let's call it W, with a whole bunch of indices, M, N, R, P, Q, I don't know, what's another letter? Z. That's a terrible notation. You're not supposed to do that. M, N, R. And now, that's a tensor with 6 indices, a 6-rank tensor with 3 covariant and 3 contravariant indices. Let me make it a little general. Let's make a different number of upper indices and lower indices. So A, 4 upper indices and 3 lower indices. Now, if I identify an upper index with a lower index, for example, replace Z by M and sum. The result is a tensor with 3 upper indices and 2 lower indices. That's a pattern. You prove it the same way as I proved this, that when you identify upper and lower indices and sum over them, what's left over, the index structure that's left over after you've summed over M, the components still transform as a tensor, in this case with 3 upper indices and 2 lower indices. So that's a process that you can do on a tensor that creates another tensor of lower rank, smaller number of indices. For example, if you construct a tensor out of 2 vectors, let's take two vectors, v and w. Let's suppose v has upper indices and w has lower indices. That's a tensor, just the product. In other words, the components are simply the products of components. We call that TMN. If I then identify m with n and sum, that defines a scalar. What is that scalar called? That's the dot product of two vectors. It's the inner product, sometimes called the inner product between two vectors. So the inner product, and even better, supposing they're the same vector, well, we haven't defined what it means for them to be the same vector. So far, things with upper components are simply different than things with lower components. Yeah?
Can we therefore say that W you've expressed there with 7 indices is equal to a scalar times WNRA?
No, it's not a scalar times that. It could be, depending on the character of this tensor. It could be that, but it's not typically a product, no. But when you do contract, this is called contracting the indices. This process is called contracting the indices m. When you contract the index m, it simply lowers the rank of the tensor, and the remaining objects do form a tensor. It doesn't mean that this w here is some scalar times WNRA, or NRA PQ. It does not mean that. In general, that won't be true. What's that? In general, no, it's not equal to that. It may be equal to that in a special case. That's a special case, but in general, it's not true. So, yeah.
When you have one vector, when you have one index, you have vectors. When you have two indexes, does that correspond to the planes or anything?
Yeah, it corresponds to planes. Yeah. But sometimes it corresponds to planes. The tensor that we got a little bit familiar with last time, the rank 2 tensor, was the metric tensor. The metric tensor has a geometric meaning. It's simply related to the distance between neighboring points. Neighboring points mean points which are separated by differential distances. All right, so if I have a set of differentials dxm, and that corresponds to two neighboring points, and we can ask, what's the distance? What's the distance between them? The actual distance. The distance between them squared is called ds squared, and it's given by dxm dxn times the metric tensor gmn of x. Now notice, this is a special case of the rule of contracting indices. We've contracted m with m and n with n. There are no leftover indices. This is a scalar. Two contravariant indices, two covariant indices. And the metric tensor is the object which allows you to compute, if you know it, it allows you to compute the distance between neighboring points. Now, is G really a tensor? Let's check. To check, we have to see how it transforms. All right, to see how it transforms, we need to write the distance between the same 2 points, but instead of in x notation, in y notation. So all we need to do is write that dxm is equal to the derivative of xm with respect to yr dyr. Right? The change in xm is just, or the differential displacement in xm is the derivative of xm with respect to yr times the differential displacement in y. If I plug that in for both x dxm and dxn, what will I find? I'll find that this is the derivative of xm with respect to yr. That's for this one. Then this one, dxn by dys times gmn times dyr dys. All right, here's gmn, that's still there, gmn of x, that's still there. dxm and dxn, I've each replaced by dx by dy times the corresponding dy. Each one of them, dxm and dxn. And now if I take this whole thing here and call it grs of y, then my formula reads that ds squared is equal to grs of y dyr dys. In other words, we've discovered that g in the y-coordinate system is g in the x-coordinate system times these familiar factors, which are the standard factors for the transformation of covariant indices. So this is the simple illustration that the metric tensor is indeed a tensor. If you express the distance in either the x-coordinates or the y-coordinates, you'll wind up with a GRS of y or a GRS or GMN of x, and they are related by this transformation property. So that's the notion of the metric tensor. Now there's another important thing that goes with the metric tensor. Second-rank tensors like this are matrices. They have two indices. They are matrices. Think of GMN at an arbitrary point, and I won't label the point. It's a matrix. I can put G11, G12, G13, G21, G22, G23, G31, dot, 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 and so forth. It's a matrix. It's symmetric. It's symmetric. G12 is equal to G21. And it has an inverse. This is something you can prove. Matrices have inverses. What does it mean that a matrix has an inverse? It means there's another matrix that you can multiply it by to get the unit matrix. What is the unit matrix in this notation, incidentally? The unit matrix in this notation is, of course, the matrix 1, 1, 1, 1 with all zeros. That's the matrix, which is what? Yeah. Well, however many components there are. Yeah. The unit matrix is the matrix which every component is either 0 if m is not equal to n, or 1 if m is equal to n. In other words, it's the matrix representing the Kronecker delta symbol, delta mn.
There's both these lower m and n, though?
That's not right, equals, that's right. Say it again?
Should the m and n and the delta both be lower?
No. The Kronecker delta in relativity theory always has one index upper and one index lower. If ever you have a formula with two lower indices and it says delta mn, either you're doing something special and unusual and not following the usual conventions, which is okay, you're allowed to. I mean, you're allowed to break conventions if you need to. But it means it's not associated with a tensor. It's not a tensor operation. So delta nm, its components are also a tensor. Now, to say that there's another matrix. Let's call this matrix. Let's just call it G. Let's not indicate any indices at all, and let's just think of it as a matrix. There's another matrix, which is the inverse matrix, and the product of the two matrices are the unit matrix. In index notation, to write that in index notation, it's G, let's call it, let's call it R in G inverse, and now M R. Here's the rule, the standard rule for contracting indices. Take a upper index here. Now, so far, I haven't told you that I'm telling you now, the inverse matrix defines a tensor. The components of the inverse matrix define a tensor with upper indices, with contravariant indices. This is not obvious. This is not obvious. It's a theorem. I would look it up if you want. Look up the theorem that the inverse of the metric, thought of as a matrix, is itself also a tensor, or also defines a set of components which are tensor components. Now, this operation here of contracting R and summing over R is matrix multiplication. So this is the process of matrix multiplication. It gives another matrix with an index M and an index N. I've summed over R. The right-hand side here is the identity matrix, which is the Kronecker delta, M, N. That's the definition of the inverse matrix here. It's the thing which, when you multiply it by G with lower indices and then contract one index, you get the Kronecker delta. Let's see if we can find it. First of all, yeah, let's take the polar coordinates. Take polar coordinates. Polar coordinates, we had the metric ds squared is equal to the r squared plus r squared sine squared theta. No, sorry, r squared d theta squared. All right, what's G11 in this case? Let's say r corresponds to the first coordinate, theta corresponds to the second coordinate. Just one. What about G22? R squared. 0, 0. No off-diagonal elements at all. This is GMN. What about its inverse? Its inverse in this case is very simple. When you have a diagonal matrix, if you have a diagonal matrix, its inverse. Say it again?
I was wondering whether it was r squared or r. It is
R squared. Yep, it's r squared. You don't square G. Yeah, the components of the metric are already squared lengths. They already correspond to squared lengths. Yeah. The inverse matrix, the matrix that's inverse to that, is just 1 over r squared. If you multiply the two matrices together, you'll get the unit matrix. If you think of them as objects with indices and contract the R index, you'll get the Kronecker delta. Try it out. Check it out. This inverse of the metric, right? I don't know that it has I don't think it has a special name of its own. It's just called the metric with contravariant components. It's called the collection of contravariant components of the metric. If you know one of them, you know the other. If you know a matrix, you know its inverse. The inverse of the inverse is the original matrix. So knowledge of G with lower indices is equivalent to knowledge of G with upper indices. The theorem, and this is not a trivial theorem, is, and I'm not going to do it on the blackboard, the theorem is that the set of components of the inverse matrix are themselves a tensor. They're a tensor with contravariant components. So if you take the metric and you invert it as a matrix, it's a collection of components. Those components form a contravariant tensor. Right? It's another representation of the metric, since it has the same information in it, but it's just presented in a different way. Those two objects are fundamental, G with lower indices and G with upper indices, and we don't bother writing the inverse there. We just remember that when G is written with upper indices, it's the inverse matrix to the ones with lower indices. And so the identity in the sense of the equation, GMR is delta Mn. This is, if you like, the definition of the object with contravariant components. It's a, and its geometric meaning is a little more obscure. The geometric meaning of this object is clear. It has to do with the separation between points. This object you'll just get familiar with. You'll get to use it, and you'll see it does some useful things. All right, that's the idea of the metric tensor and its inverse, or the metric tensor with covariant indices and the metric tensor with contravariant indices. Now, once you have this metric in covariant and contravariant form, you can start playing games and write mappings that relate covariant and contravariant vectors. In fact, you can define for every covariant vector, or for every set of covariant components, you can define a set of contravariant components and think of it as contravariant and covariant components of the same vector. Here's the rule. If I give you a set of covariant components, I can construct from it together with the metric tensor. Well, let's start with contravariant. I can construct from it and the metric an object with a lower index. By multiplying it by GMN and summing over M, that gives me a new thing which I'll call V sub n. If I know V with a superscript and I know the metric, let's say the metric is given. The metric is given knowledge. It's a piece of the geometry of space. If I know V and I know G, then I can reconstruct a corresponding set of components with lower indices. You can just think of this as the representation of the same vector except with a lower index. Now, what is the connection between them really? I'll tell you now. The connection between them is what I told you in the first place. The connection between these two things is if Vm are the set of coefficients that you multiply by unit vectors and sum them up to get the vector V. If you think of these V's here as defining a vector by adding up the V's times unit vectors, then the V's with lower components are, as I told you in the beginning, the covariant components of the same vector. In other words, the projections onto the axes. These are the set of coefficients that you use to expand the vector. These are the set of orthogonal projections onto the axes. So they're really representations of the same object, two different representations, and they're related in this form.
Question?
Yeah.
Going back to the other
lots of work. Can't there be tensors that don't have inverses?
There are, but the metric tensor is never one of them. Let's not prove that now. It follows from the fact that G is symmetric and that there are no directions in which the vector has no length at all. There are no zero eigenvalues of the metric. Right, but that's a good question. It's a fair question. Let's just take it as a rule that the metric tensor always has an inverse. And we'll see. I'll come back to it. I'll prove it for you another day. I hadn't thought about it, but it's an easy thing to prove. Yeah.
Is that also true in relativistic, where you have a minus?
Yeah, it is. It is. It is. It's still true. Yeah.
On the upper board there, it can be shown, on the left, the upper board on the left, it can be shown, right? That
Yeah.
the s squareds are the same regardless of the coordinate system. The
Yeah.
distance is in fact the same.
Wait, say it again?
The distance, the
Yeah.
ds will be the same regardless of the coordinate
Yeah.
system. It's not obvious in the expression, but I assume it can be shown.
Wait. That the ds squares are the same?
The s squared is the same whether you compute it with the gmn or the gr.
No, that is where we got we assumed that to find the relationship between gmn of x and grs of y. In other words, I simply took this and rewrote it in this way. It's really the same equation. Yeah. Given that the g's are related, as they have to be related by tensor transformation properties. Yeah. Yeah.
You said that G was symmetric. Is that clear from what we
Good question. All right, so let's see what it would mean for them to not be symmetric, and then see why. The answer is it doesn't matter whether you choose them to be symmetric or not, but let's see why. All right. What does G12 multiply? G12 multiplies dx1, dx2, right? What does G21 multiply? Multiplies dx2, dx1. But really, what that means is that the only thing that comes in when you calculate ds squared is G12 plus G21 dx1, dx2. Only the combination G12 plus G21 enters into anything. That means you can take G21 and G12 to be equal to each other and sort of divide it symmetrically between dx1. There's a piece in the metric which has dx1 multiplying dx2. Right? You could call it all coming from G12 if you like, or you could call it all coming from G21, but the convention is to split it equally between G12 and G21, and therefore make the G symmetric. So it's partly a convention, but it's a useful convention. And right.
So the general rule would be that G12 is not the same thing as G21. Generalized.
You could imagine generalizing things that way, but then the difference, the non-symmetric piece would never come into anything. Right? Supposing G12 and G21 were the negative of each other, then this would just cancel out. And so you just wrote something redundant that you didn't need. So there's no loss of generality in taking it to be symmetric, but you don't have to take it to be symmetric. If you don't take it to be symmetric, it's not clear there's always an inverse. Matrices with, well, I'll come back. I'll come back to the question of the inverse next time. I don't want to interrupt it right now. Okay, so the metric allows you to play new games where you take tensors and shift the index from upstairs to downstairs, and think of them as the same object except covariant components and contravariant components. It allows you to find a one-to-one correspondence between a set of contravariant components and a set of covariant components. And you're free to think of them as the same thing since they have the same information. Incidentally, you can solve this equation for the upper components. This is the lower components written in terms of the upper components. See if you can prove, using the property, where is it? Using only the property that G, what is it, MRGRN equals delta Rn. Oh, sorry. Mn. See if you can prove, it's very straightforward, that you can solve this as Vm equals Gmn with upper index times Vn. Really all it is another way of writing in matrix language. It would be G times, do it. It follows immediately from this equation over here. Okay. Right. Yeah, all you have to do is take Vn from this equation, plug it into here, and you'll get an identity that Vm equals Vm. You do it. Okay. So you can go back and forth symmetrically between things with upper indices and lower indices, and the process is called raising and lowering indices of tensors. So every tensor has multiple identities in which you can raise and lower any of the indices at will. Keep track of them. Keep track of which ones you've lowered and which ones you've raised. For example, if I have a general tensor Tmn, I can raise the index m. How would I do that? I would multiply it by Gmr Trn. I've taken the first index on the left here, and I've applied the trick to the first index to raise it. And what does this give me? This gives me an object that I can call Tmn. So I can raise and lower the indices and of course, the objects that you get are different when you raise and lower them, but they're collections of objects which have the same content as the original starting ones, since you can go back and forth freely between them. All right, that's the sense in which vectors have, in which a vector has both covariant and contravariant indices. All right, that is basic tensor arithmetic, tensor algebra, I guess one would say. Upper indices, lower indices, transformation properties of the indices, and the metric tensor that allows you to raise and lower indices. In particular, take the object dxm. That stands for a little interval dx, a little vector. I can assign it, and it's natural to think of the little interval as having contravariant components. But you could also define an object dx sub m, the same vector, by writing it as gmn dxn. The natural thing to define to start with is the contravariant components. Those are just the little intervals dx. But then nothing prevents you from constructing the covariant version of the same object. And this is the way you would do it. Now, before I told you earlier that if you have an upper index and a lower index in a tensor, you can contract them. So let's take a new tensor. Let's take a tensor which has an upper and lower index. And it's made just by multiplying dxm by dxn. That is now an object with indices m and n. It's a tensor. And now I want to contract the index m with n and get dxm dxm. What happens when you take a tensor with two indices, one upper and one lower, and you contract them? What do you get? A scalar. So this object is a scalar, but now let's rewrite it. Let's rewrite it by using that these x with the lower m is g mn dxn. That means that this object here is dxm. Well, let's change. Let's write it this way. N. Yeah, no, it was right. dxm. It's clearly dxm dxn gmn. This object is just the dx with the lower index. I lowered the index of dxn, that's here, and I multiply it by another dx. So what is this object with one dxm upper and one dx lower contracted? It's gmn dxm dxn. What is that? It's ds squared. It's the distance between them. So by using the metric tensor to lower the index, you can write the distance formula in two distinct ways. You can write it gmn dxm dxn, or you can just write it dxm dxm, one lower and one upper. Same thing. This is a little more condensed. This is a little more explicit.
Would you go back over that first equation you wrote, dxm superscript and then subscript?
Here?
Yes, and you ended up making those equal to a scalar.
Sorry, I didn't mean to write equals. I just meant goes to by contracting the indices. I did not mean to write an equation. I simply meant that you could contract the index m and n and construct the x with superscript, the x with a subscript, and this is a scalar. Okay? This doesn't transform. It's an invariant quantity, whereas the things that it was built out of transformed, but then you contracted the index and got a scalar. Okay, so there's two distinct ways. In fact, there's another way that you could write the metric. Another way you could write it, a third way, is to write two lower indices, dxm, dxn, and that, what would I have to multiply it by? G with upper indices, indeed. That's also equal to the same thing. They're all equal to each other, and they're all equal to the distance between the points, which are separated by the differential displacements dx. All right, that's the basic idea of the metric and simple.
Significance of the g's in that relationship?
Where? Say it again.
That you could do your orthogonal projections. Now, is there, can you see in those terms?
The gmn in the top equation, the bottom equation, lower board.
Yeah.
Gmn.
Yeah.
Those. Is there any correlation between those, the upper and the lower subscripts?
Here?
The gmn,
Yeah.
and then the gmn in the third equation.
Oh, they're all summation indices, so it doesn't matter what you call them. Yeah. As long as it's summed over, it doesn't matter what you call them.
But is there a relationship in the values of them? Like, are they like inverses? Or
Geometrically, how do they?
Well, this is the inverse matrix to this. So you have to know how to construct inverses of matrices. All right? For simple diagonal matrices, the inverses are easy. You just turn the entries upside down. For things with off-diagonal elements, it's more complicated, and you have to consult the book or use a computer program or or whatever. And in particular, for 4x4 matrices, it's no picnic. For 2x2 matrices, it's always easy. But good. All right. So that takes us through tensor arithmetic, tensor algebra. Incidentally, there are some other operations you can do with tensors that may give you tensors. I haven't exhausted all the operations that you can do that give you tensors. You can add tensors. Add two tensors, but when you do, you had better make sure they're tensors of the same type. In other words, you would not want to add TMN plus WMN. That's a nonsense expression. It has no distinct transformation properties. This transforms one way, this transforms the other way. For example, if this happened to be 0 in one set of coordinates, it might not be 0 in another set of coordinates because the t's with the lower indices don't transform the same way. If a tensor is 0, if its components are all 0 in one coordinate system, there's 0 in all coordinate systems. Why is that? Let's just look at the sorts of things. Well, that's because if we have a tensor with any number of indices upstairs and downstairs in the y coordinates, it is equal to a bunch of dx's times dy's and dy's times dx's of various kinds times the corresponding tensor in the x coordinates. If it's 0 on one side, it's 0 on the other side. So if a tensor is 0, in other words, if the tensor being 0 means all of its components, if all of its components are 0, then it follows they are 0 in every coordinate system. So a tensor being 0 is an invariant statement about that tensor. All right. Another way to say the same thing, perhaps it's saying something a little different, but almost the same thing, is that if two tensors are equal in one coordinate system, let's say t equals w, mn in the x coordinates. That also says, of course, that the difference between them is equal to 0. Then the difference is going to be 0 in every coordinate system, which means that the tensors are equal in every coordinate system. So once you prove a tensor relationship, namely that the left-hand side of an equation is equal to the right-hand side of an equation in one set of coordinates, it's true in every set of coordinates. That's one of the powerful things about tensors, that it allows you to make statements such as one thing is equal to another, although each side of the equation may have complicated transformation properties, you can be assured that both before and after the transformation, they will remain equal. That may not have come out right. You can be sure that if they are equal in one coordinate system, they will be equal in the other coordinate system. That's part of the power of the equality of tensors is a geometric fact which doesn't depend on the coordinate system. The components of the tensors are things which do depend on the coordinate system. Okay, now let's take a little bit of a break and then come to tensor calculus, which is harder than tensor arithmetic and tensor algebra. I was going to start the subject that I call tensor calculus, which means the study of how you differentiate tensors. Of course, you can just differentiate them, but then it's not clear that you get tensors when you differentiate the components of a tensor. And in fact, you don't. You have to do something smarter than just differentiate the components of the tensor to get the component. The derivatives of the components of tensors are not ordinarily components of tensors. Did that make sense? The derivatives of components are not themselves components of tensors.
Derivatives with respect to what?
Hmm?
Derivatives with respect to what?
Position, x's. But I think I won't do that now. I think instead, we'll do that next time. And I think I would like to get to space-time. We've been talking about space, 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 and we have not been talking about relativity. We've been talking about space. So I think we're all set up in a way that allows us to jump straight into space-time. And then somebody asked me what the meaning of saying that the universe is expanding, what does that mean? And I think we can probably do that yet tonight once we introduce the idea of space-time. Now, to introduce the idea of space-time, we have to go back to special relativity. Special relativity is a subject that you can learn in 3 days. I assume that we all know it, and if not, we can all learn it quickly. I think if you've been in my class, you've taken special relativity a couple of times already, at least 2 times, maybe more. And I'm going to assume that you have a basic understanding of Lorentz transformations. But even if not, I think we're set up in a manner that allows us to sort of make quick work of it. First, let me just make some remarks about ordinary space. Even if I am only going to use, even if I am not interested in curvilinear coordinates or curved space, all I'm interested in now is Cartesian coordinates. There are still more than one Cartesian coordinate system that we can use to describe space. Even if I place the origin of coordinates and nail it to the center of some place, there's my origin of coordinates, I still have not fully specified a set of coordinates by saying they're Cartesian. Here's a set of Cartesian coordinates. Here's another set. Well, I meant to place the origin at the intersection of the axes. Here's another set. Can that be seen? And they're just related by rotation of the coordinates, of course. Rotation of Cartesian coordinates is a special case of transformations between x coordinates and y coordinates. Another thing you can do is translate the coordinate systems, keep them parallel, but translate their locations. Those are also coordinate transformations. In neither case do they correspond to curved coordinates, curvilinear coordinates, but they are coordinate transformations. And all of the rules we've set up till now hold. The only thing is that in all of these coordinate systems, the metric tensor has the same form. The metric tensor is just the Kronecker delta. In other words, ds squared, let's talk about 2 dimensions for a moment, is just equal to dx1 squared plus dx2 squared. That's the same as saying that the metric tensor GMN is equal to the Kronecker delta, delta Mn. Now, I said that, strictly speaking, delta Mn with both of its indices lower is not a good tensor object. it is a good tensor if all we're doing is translating between one set of the Cartesian coordinates and another. For curvilinear coordinates, this equation would be nonsense, but if we're just translating between Cartesian coordinate systems, just rotating them or translating them, then in every such coordinate system, the metric is just dx1 squared plus dx2 squared, which I can also write as delta mn dxm dxn. In Cartesian coordinates, there's no difference between upper indices and lower indices. They're the same things. So there's a lot of simplification. But there's another way to say this, that the transformations, the class of transformations that takes you from one coordinate system to another are the transformations which preserve the form of the interval, preserve the form of the length, preserve the form of Pythagoras' theorem. Right? That the s squared, the length of an interval, is dx squared. And what happens if I have more components? I just add more of them in. Dx3 squared and so forth. So the ordinary transformations that you can do on Cartesian coordinates are the transformations which preserve the form of the simple sums of dx squares as the length interval. Now let me come to space-time. As you know, and if you don't, you better find out quickly, space-time has 4 coordinates. It's a 4-dimensional space. One of the coordinates is time. Incidentally, we are always going to work in units in which the speed of light is equal to 1. Now, there's a notion in special relativity of the proper time, or of the interval separating 2 points. Space and time will work with speed of light equal to 1, except when I say that we won't. And we can consider 2 points. For example, these could be 2 points on the trajectory of a particle. There's a notion that we've discussed in previous quarters of the idea of the proper time interval between 2 points, which is very similar, but a little different, but very similar to the distance between 2 points. But you might expect, if you were naive, that let's say there's only 2 dimensions, one space coordinate and one time coordinate. You might write ds squared is equal to dt squared plus dx squared. And you could write that. That's a possible definition of something. But it's not the right thing for relativity theory. In particular, the Lorentz transformations, the things which transform you from one frame of reference to another, are not the transformations which keep this invariant, but keep something else invariant. What is it? dt squared minus dx squared. And that's called the proper time, often labeled by d tau squared. If we insist on taking the speed of light not to be 1, then the speed of light goes into this equation in the denominator over here. But in special relativity, not using c equals 1 is as stupid as using meters for x components of vectors and inches for y components. If you did so, think about what your equations would look like. You would have some crazy factors appearing all over the place. First of all, your equations would not look rotation invariant, and they would have all over the place peculiar numbers, which were simply the conversion factor for the units that you use for x dimensions and for y dimensions and z dimensions. The speed of light is very much like that. It's a conversion factor from units of length to units of time. Choosing c equals to 1 is the natural analog of using the same units for x measurements as y measurements. Right. Now, notice, incidentally, if I talked about the distance between 2 points, and I measured x in different units than y, would the distance be dx squared plus dy squared? Let's suppose I measure y in inches and x in, let's say, feet. And now I want the distance between those 2 points in feet. What would I have to put there? If I want the distance in the ds squared, if I want it in feet, and x is measured in feet, then I'll have dx squared. But what about dy squared? Y is measured in inches. Yeah. Right. Plus dy squared divided by 144. You have a stupid factor of 1 over 144 multiplying the dy squared term, basically the same silly factor that's here. If you use units in which the speed of light is equal to 1, it's the same thing as using meters or inches for yeah.
I think I read somewhere that particle physicists use units in which electron volts is everything. Measured in electron volts?
Yes. Well, you can.
How does that work? I mean, how do you get length and time for the electron?
You need the Planck's constant, which isn't in here yet. The speed of light normally you say there are 3 distinct units that you need: length, time, and mass. Okay. Now, given that the speed of light is equal to 1, or assuming the speed of light is equal to 1, it eliminates one of these. Setting Planck's constant equal to 1 will allow you to write masses in the same units as you use length and time. All right, but we're not going there today. We're not going to quantum mechanics today. Today, we're just going to set c equal to 1. So, and now, Lorentz transformations and the special theory of relativity is simply the theory of transformations or coordinate systems which preserve this form, dt squared minus dx squared. Coordinate transformations, space-time coordinate transformations, which preserve the form of the metric. This metric now represents proper time, not spatial distance necessarily. It can also represent spatial distance, but it represents what it represents. And the Lorentz transformations are transformations from one set of coordinates to another set of coordinates in which, in both sets of coordinates, the form of d tau squared is equal to dt squared minus dx squared. Now, I've written it for 2 dimensions. What if there are more dimensions of space, as there really are in the real world? Then it will be d tau squared is equal to dt squared minus dx squared minus dy squared minus dz squared, or whatever, if there are 3 coordinates of space. Okay, so that's it. That's all you have to know about special relativity. It's the theory of transformations which preserve a length element, which is a funny thing with a minus sign in it. Now, we're going to assume that everybody knows that, and we're going to move on. What we're going to say is, supposing I introduce curved coordinates into space-time. Have we ever seen any examples of curved coordinates in space-time in this quarter so far? Yeah, accelerated coordinates were examples of curved coordinates in space-time. I gave you coordinates which look like this, And we also talked about coordinates which were accelerated. There's an example of the introduction of curved coordinates into space-time for a particular purpose in order to study accelerated coordinate systems. Okay. So it's not insane and not silly to introduce curved coordinates into space-time. And if you do, what's going to happen to this formula? What's going to happen to this formula is the same thing that happens to the formula for distance between points when you introduce curved coordinates into space. Namely, you're going to get some new coefficient functions, and the formula is going to look like, well, first of all, notation. There are 4 coordinates of space-time, t, x, y, and z. We're going to label them x mu. Whenever you see a Greek index as a coordinate index, it always means that you're talking about space-time. Okay? And what does mu run over? Mu runs over 4 possibilities, 1 of time and 3 directions of space. Okay? The usual convention is not to call it x1 through x4, but to call it x0. I don't know how that got started. Why x0 through x3 rather than x1 through x4, I don't know. With x0 being the time coordinate. Time first.
Or you start with space, you got 1, 2, 3. What are you going to do, add 4? Why not add 0?
Yeah. Right. If you decide you want to make higher dimensional space-times, you add more space components. You never add more time components. I mean, you could play with that if you like, but oh yeah, sure. Anyway, so what's the natural generalization of this formula when you introduce new sets of coordinates? Let's call them y mu now, which also has a time component and 3 space components, and assume that the y coordinates and the x coordinates are related to each other by coordinate transformation. Then what's the natural analog, or the generalization, I should say, of the simple special relativity formula? It's exactly what you might expect. D tau squared is equal to g mu nu of. Now, when I write just of x, it means of space and time. A general function of position in space-time is just written as a function of x, without specifying whether we're talking about x0, x1, x2, x3, and so forth, times dx mu dx nu. We don't need to have real, genuine curvature and gravity and so forth to do this. We could just do this by introducing curvilinear coordinates for x and t. So at the moment, we haven't introduced the theory of gravity when we say we can write this down. We're just generalizing the allowable coordinates that we can play with. So that's the general form of the proper time element between 2 points in space-time, where space-time has a metric tensor. Now, what is the metric tensor? Let's call these simple coordinates like this. Let's call these. Should we call them Cartesian? What's the right term for? You have a name for them? Minkowski, good. Minkowski coordinates, yeah. Ordinary Minkowski coordinates. And Minkowski coordinates are not unique. Just like Cartesian coordinates are not unique, you can rotate them, you can translate them, you can Lorentz transform Minkowski coordinates. What's the Minkowski form for the metric tensor? Well, it's clear. It's of the form 1 for the dt squared, and -1, -1, -1 for the dx squared. In other words, it's a matrix, just like G was a matrix before. In flat coordinates, originally the metric was 1, 1, 1, whatever. What is it now? It's a 1 and 3 minus 1s, with all zeros elsewhere. All right. So a special case of a metric tensor, of a formula like this would be where G mu nu was simply 1, minus 1, minus 1, minus 1, in which case you would reproduce the usual Minkowski proper time. Okay. This symbol has a name. It's the analog of delta Mn. But it's not delta Mn. It's not 1, 1, 1, 1. It's 1, minus 1, minus 1, minus 1, minus 1. It has a name. It's called eta. Eta Mn. Greek letter eta. So eta is the metric of space-time in Minkowski coordinates. And it's 1, minus 1, minus 1, minus 1, minus 1. And so we could write in Minkowski-type coordinates, the analog of Cartesian coordinates, d tau squared is equal to eta mu nu dx mu dx nu. Okay. That's space-time in a nutshell. Almost everything we said about tensors, their transformation properties, is still correct. G mu nu also allows you, it has an inverse again. So G mu nu has an inverse matrix. G mu nu and its inverse allow you to raise and lower indices. The transformation properties of tensors are identical to what they were before. I'll write them again. You have things like dx mu, which have a contravariant structure. They're related to dy mu by partial of y mu with respect to x nu dx nu. So this defines the transformation properties of contravariant indices. It's exactly the same as it was before. The transformation properties of tensors are exactly what they were in the pure space case. You don't have to change it, not at all, for both contravariant and covariant indices. The only thing is that the metric tensor typically has minuses as well as pluses in it. Now, what are the special rules about how many minuses and how many pluses? We'll come to that. But this, for example, is a special case, 3 minuses and 1 plus. I'll be more precise about what's an allowable tensor, an allowable metric tensor. But for now, the rules are almost exactly the same, with the Kronecker delta being replaced by eta.
When you did the transformation of x and y, you said y super 0 was the time dimension. What do you mean by that?
Just a definition of just a notation.
Okay, even though
X super 0 equals is t.
Transform from x, so I mean, one transformation could be you could just reverse, let's say x and t, and then you would say the new x would be the time dimension.
Yeah, you could do that. You can do it if you like. You can do it if you like. It even happens in some situations that you might want to. Now, there is a rule. I'll tell you what the rule is now, and we'll go through it another time. But we do need to go through it. The rule is that G mu nu is again a symmetric tensor. Symmetric tensors have eigenvalues. They have a complete set of eigenvalues. They will always have 4 eigenvalues. For an ordinary space, those eigenvalues are all positive, and it corresponds to the fact that spatial distances are always positive. In relativity, there is always 3 negative and 1 positive eigenvalue. All right? If you're writing something down which has not the right number of positive and negative eigenvalues, you have some sort of pathological space. But we'll come to that. We'll come to that. For now, the rules are really unchanged. The rules are really unchanged, apart from the fact that, that a typical metric will have some minus signs and some plus signs, and in terms of eigenvalues, there are always 3 negative ones and 1 positive one, which means is, yeah. It is its own inverse, yeah, just like the Kronecker delta is. Right. So the eta with the upper indices is the same as the eta with the lower indices, right? Right, I'll go through this. I will go through this again, but I just wanted to, since I was asked a question about how to think about the geometry of an expanding space-time, let me answer it right now. We have everything we need now to write it, to express it. In a general space-time, these metric components are functions of all of the coordinates. A particularly simple kind of space-time is one where the coordinates, where the metric only depends on time and doesn't depend on space. That's the sort of situation you have when space is homogeneous. If space is homogeneous, everywhere the same, that's a typical cosmological setup where space is everywhere is the same, apart, of course, when I say it's everywhere is the same, I mean on very large scales, on scales much bigger than galaxies and so forth. Space is the same one place as another. The metric doesn't depend on space, but it does depend on time, and that time dependence is the expansion of the universe. So let me write down for you a particular metric, and then just look at it a little bit. It corresponds to G mu nu is equal, instead of 1 minus 1 minus 1 minus 1, let's write 1, 0, 0, 0, 0. Now instead of minus 1, let's write minus a of t, where a of t is time dependent. 0, 0, 0, 0 minus a of t, 0, and 0, 0, 0 minus a of t. One function a of t, just one function, and that function is called the scale factor. What this means is that the proper time, or the line interval, is dt squared minus a of t squared dx squared. Dx squared plus dy squared plus dz squared. It may not be obvious to you, but this space-time with a time dependence here is very different than flat space-time. To show you the kind of difference, supposing we did something similar with space. Incidentally, this is the characteristic metric. If a of t is an expanding function of time, if it's an increasing function of time, then that's called an expanding universe. Right. I'll come back to this, but let me just show you qualitatively what this means by giving you the analog for ordinary space. Let's just think about 2 dimensions of space, and let me imagine one of the directions is an angular direction. We've already done things like that. We considered dr squared plus r squared d theta squared. Dr squared plus r squared d theta squared. That's somewhat similar to this. The r squared is like dt squared, and r squared itself is like a squared. It's a function of t. A is a function of t. Here, r is a function of r, or r squared is a function of r. So there's a similarity between this formula here, dt squared minus a of t squared dx squared, and the r squared plus r squared d theta squared. Now what is the space-time here? Oh, sorry, what is the space here? It's a plane. It's just polar coordinates. It's a plane. It's flat space-time, and it's just looking at that space-time in polar coordinates. But now, supposing instead of just r squared, I put some general function of r in, First, before putting a general function in, let's put in another specific function, sine of r squared. What is this space now? That's a sphere. And the way to think about it now is that the distance around the distance around the theta axis depends on r in a characteristic way. Here's the sphere. Let's think of r as, r is now like the polar angle. And as you go around the sphere, or as you go around the theta direction, theta I'm having go this way now. I think I've turned the sphere on its side for some odd reason. Why did I do that? It was stupid. Let's stand it up again. Theta goes around this way. And r is just replacing what I called phi before. Right? What's happening is instead of sine of r just increasing like r, it increases and then it decreases. Sine is a function which increases and then decreases, right? It increases from 0 to pi over 2 and then decreases. That's why the sphere increases and then decreases. Right? It starts growing as you move away from the South Pole. It starts growing but then shrinks again. That sphere, of course, is not a flat space-time. If I only had r squared here, it would be like looking at just a plane. With sine squared here, it's more complicated and it's curved. Okay. Supposing I put an arbitrary function, some kind of function which, I don't know, let's put an exponential function here, e to the 2r. What kind of space would that look like? It would look like a horn. Yeah, it would look like by a horn, I mean, toot toot. The distance around the theta axis would grow exponentially, and it would look like that. Now, it's not growing with time, it's growing with r. So this would be some kind of space which had the property that as you move away from r equals 0 is over here, it grows, and it grows rapidly, grows exponentially. Supposing I put in, I don't know, you could put in all kinds of things. I don't know, e to the 2r times, I don't know, some arbitrary function which grows and at the same time oscillates. It grows and oscillates at the same time. Well, you could make very complicated kinds of spaces which look like that. They're just surfaces, but the character of the surface and the way that it grows as you move away from r equals 0 depends on this function f of r. Most of these spaces are not flat. They have curvature of all kinds that we'll talk about next time, but that's exactly what this a of t does here. It creates a space-time which, as a function of time, the space-time grows. Grows, shrinks, does whatever it does. Can do all kinds of wiggles. And instead of r, this will be t. So this is the metric of a time-dependent space-time. And if a is a growing function, then it's an expanding space-time. That's all it means to say that space-time is expanding in this language of a metric tensor. We'll come back to it. Next time we'll talk about curvature and parallel transport and try to get to the Einstein equations.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.
Rarely catch a glimpse of the thieves. Many don't even know they've been victimized until it's too late.